Hi, welcome to another lecture on ME 605. So in this lecture, we will continue discussing about finite difference method. Okay. So in the last lecture, we discussed that there are two stages in obtaining numerical solution of governing equation to a physical problem. Okay. The first step involves discretization of the governing partial differential equation, which gives rise to a system of linear algebraic equations. Okay, no matter whether we use finite difference or finite volume or finite element, discretization will convert a partial differential equation into a system of linear algebraic equation, which is okay. Let us denote u as our unknown a u times p. Okay, a is system matrix. Okay, u is vector of unknowns and b is the source term. It's a vector containing the source term. Okay, also we have discussed for a very simple example problem how to obtain system matrix and the vector containing source term, and also we discussed about properties of the system matrix in the last lecture. Okay, recall that the accuracy of the solution process is predominantly dictated by the discretization process, but the execution speed of your simulation is dictated mainly by the equation solver part. Okay, how do we solve the system of linear algebraic equation to obtain the exact solution? Okay, so this is the focus of this lecture. Okay, we are going to talk about various methods that are available. There are thousands of methods. We are going to discuss some basic methods to obtain numerically the solution of the system of linear algebraic equations. Okay, and that's the focus of this video lecture. Okay, so there are two classes of method available for the solution of linear algebraic equations. Okay, there are two classes of methods. Okay, so the first one is called direct methods. Okay, we will discuss about these methods in detail. The second one is iterative methods. Okay, so direct methods involve something like Cramer's rule, okay, and Gauss elimination, for example, and LU decomposition. Okay, these are all some examples of direct methods, and iterative methods include Gauss-Jacobi, Gauss-Seidel, or something called successive over relaxation, method, multigrid, etc. Okay, these are all some examples of iterative methods. Okay, we will pay more attention to these methods in this lecture. Okay, so let us start with direct methods. Okay, so let us look at how these methods work first and discuss their characteristics after that. Okay, let us start with Cramer's rule. Okay, this is one of the most elementary methods that is taught usually in high school mathematics. Okay, you have all learned about Cramer's rule in high school mathematics. Okay, so the solution of A equals B using Cramer's rule can be written as, so u, the ith component of u is a vector. Okay, so ith component of u is given by determinant of ai divided by determinant of a. Okay, where you know what is a here is. Okay, a is the system matrix, okay, which is here, and ai is the matrix obtained by replacing ith column of A with B. Okay, so for example, let us take a very simple example here. So let us say 3u plus 4u2 is 7, 9u1 minus 7u2 equals to 2. Okay, so this tells you that A is 3, 4, 9 minus 7, which are found by coefficients of the unknowns appearing in the corresponding equations. Okay, the unknown u is a vector which contains only 2 elements, and the source term B is the right hand side, which is 7 and 2. Okay, now the solution can be found simply by computing determinant of A1 by A and A2 by A. Okay, where A1 is obtained by replacing the first column of A with the right hand side. Okay, so that would be 7, 2, 4 and minus 7. Okay, A2 is obtained by replacing second column with the right hand side, which is 3, 9, 7, 2. Okay, it's a very simple method, right? If you know A1 and A2, you can compute the determinant and calculate U1 and U2. Okay, if you see the characteristics of the method, this is very robust. Okay, by robust mean we can obtain solution of any non-singular system of linear algebraic equation. Okay, we can find solution of any non-singular system of equations. Okay, that's what we mean by robust, applicable for majority of the cases. Okay, but it has a huge problem that it is extremely inefficient. Okay, it becomes extremely inefficient for large matrices. Okay, we have seen an example just with 2 elements, but if you increase the size of the matrix, it becomes very inefficient. It means that the number of, to quantify what do we mean by inefficient, we can write that the number of arithmetic operations involved is proportional to n plus 1 factorial. Okay, where n is the number of equations. Okay, so which means that if you have 10 equations, just 10 equations, it requires 4 into 10 to the power 7 operations. Okay, so if you have 10 equations, the number of arithmetic operation involved is proportional to 11 factorial, which is approximately 4 into 10 to the power 7. Okay, so assume that you have a laptop with 1 gigaflop per so you have a laptop of 1 gigaflop. Okay, for laptop of 1 gigaflop, you can solve this using within a fraction of a second. Okay, I hope you all know that by flop we mean number of floating point operations the computer can perform per second. Okay, so by gigaflop we mean 10 to the power 9. Okay, so if you say gigaflop, the computer can perform 10 to the power 9 floating point arithmetic operations per second, but solving 10 equations require 4 times 10 to the power 7 operations, so this can be computed within a fraction of a second. Okay, but just if you increase the equation to 30, just 30 equations, okay, you require approximately 8 into 10 to the power 33 is the number of operations required to solve just a system of 30 linear algebraic equation. Okay, now I'll tell you, I'll give you a to do here, or something that you have to check. Okay, go to top500.org. okay, so this website gives you list the world's fastest 500 supercomputers. Okay, take the world's fastest supercomputer and compute how many years it will take to solve this. By world's fastest supercomputer. Okay, you have to do it. It will give you an idea of how inefficient Cramer's rule is. Okay, right. So the bottom line here is that Cramer's rule is not meant for CFD. Okay, where the number of equations can be very easily 10 to the power 5. Easily 10 to the power 5. Okay, to solve just 30 equations, it can take years. So you can imagine, if you have number of equations to be of the order of 10 to the power 5, how many decades we have to wait to get the solution. Okay, so Cramer's rule is not meant for CFD. Okay, the next one we discuss is Gauss elimination. Okay, so you have learned this recently in your numerical analysis course. I will not go into full details, but I'll briefly explain the process behind Gauss elimination. Okay, so let us consider a system of linear algebraic equations expressed in matrix form. Okay, I will expand the matrix now so that we can clearly discuss the process involved. Okay, so let us write the system. Let us expand the system matrix and write. Okay, so these are all coefficients of the system matrix, A and N. Okay, we have n equations. So I think I am using interchangeably small n Kaplan here, but I hope you will be able to get the full picture. Okay, so this is the system of linear algebraic equations that we want to solve. Okay, and Gauss elimination involves 2 steps. Okay, you know them already because you have learned this very recently. Okay, so step 1 is what do we call as forward elimination step. Okay, in forward elimination, we perform a series of row operations and convert the system into an upper triangular matrix. Okay, so in forward elimination, we perform a series of row operations which will make sure that the system matrix is converted into upper triangular matrix. Okay, so this equation system becomes something like this. So A11 dash, okay, let that diagonal. So A22 dash, A33 dash, and AN dash. By dash we mean these the magnitude of these coefficients are modified in this process. Okay, okay, by upper triangular matrix we mean that all entries below the main diagonal is 0. Okay, if the matrix contains non-zero elements only on and above the main diagonal. Okay, so then un, and correspondingly the source term also, the magnitude gets modified. Okay, by dash we mean their magnitude gets modified during the row operation process. Okay, so this is the forward elimination step. Convert the full matrix into into an equivalent system in which the system matrix is upper triangular. Okay, so these two systems are actually equal. Okay, we just scaled up the equation and modified the equation just by performing linear operations. Okay, these two are actually equal. I mean, by solving these two you will get the same u values irrespective of which one you choose to solve. Okay, that is the first step. The second step is the back substitution. Okay, so the solution of the above equation, this one that has the upper triangular matrix as the system matrix, is much easier than the original one, because the last equation here has only one unknown. Okay, so the last equation has only one unknown, which is a un dash. Sorry, un doesn't have a dash, becomes b n dash. Okay, from here you can compute a n dash. Okay, and if we consider the n minus 1 equation, okay, that will have two terms, a n minus 1 n, a n minus 1 n minus 1 u n minus 1 plus a dash u n dash is b n minus 1 dash. Okay, so here in the first step we have computed un dash. Sorry, un doesn't have a dash. Okay, in the previous step we have computed this one. Okay, we know these coefficients, and the only unknown here is un minus 1. Okay, okay, this is wrong. We compute un, not a n dash. Okay, by successive substitution like this, starting from the last equation, we will be able to compute all the components of un, because once we start back substitution, every equation will have only one unknown. Okay, so this is very straightforward. So successive substitution starting from the last equation. So this will give us all the components of the unknown. Okay, so back substitution is very easy to understand. Okay, so here when the number of operations involved are proportional to n cube, where n is the total number of equations. Okay, so for Cramer's rule it is n plus 1 factorial. Here it is just n cube. So this is faster than Cramer's rule. Okay, so looking at these two models, the name direct method is very clear. Okay, so why do we call them direct methods? Okay, the reason is that once the system of linear algebraic equation is given, we obtain solution to that by performing a series of arithmetic operation in a countably finite number of operations. Okay, so for we obtain solution in a countably finite number of operations. Okay, once you know the matrix size, you know how many operations you need to get the solution. Okay, so they are called direct methods because we directly know the amount of work involved. Okay, but there are very serious disadvantages associated with direct methods. Okay, so the disadvantages of direct methods are their poor efficiency, and their demand for a very large, I would say huge, computer memory to solve the problem. Okay, so then the term numerical method and computational method are used always in with to mean numerical. Okay, so all numerical methods are also called computational methods. The reason being that without the availability of computers, the usefulness of these methods are highly limited. Okay, we never solve Gauss elimination process or any of the numerical methods that you have learned in numerical analysis course by hand. Okay, all these are solved always in a computer. Okay, so the main disadvantages of direct methods are their poor efficiency and demand for very for huge computer memory. This I will explain now. Okay, so the efficiency part is very clear by now, because although the Gauss elimination has the number of operations required to be n cube, which is smaller than Cramer's rule, it is still very expensive. Okay, the demand for huge computational memory requires some discussion. Okay, so we have discussed in the previous lecture that the system matrix is sparse. Okay, by sparse, do you remember what do you mean by a sparse matrix? That they contain major number of zero entries. Okay, so if you take the matrix that we have obtained from our example, which is study one-dimensional heat conduction problem, they have non-zero elements only along 3 diagonals. Okay, and all other entries are 0. Okay, so if we have n unknowns, the matrix size is, I think we already discussed this, the matrix size is n square, but the number of non-zero entries are, for a 1D problem, is usually 3 times n. Okay, and for a 3D problem it will be 7 times n. Okay, so major or majority of the elements appearing in the matrix are 0. Okay, such a matrix is called sparse matrix. Okay, but direct methods cannot exploit the sparsity of such matrices. So direct methods do not exploit this sparsity in their solution process. Okay, which means that all the n square entries need to be stored in the computer memory. So all n square entries, which majority of them are 0, need to be stored in their memory. Stored in the computer memory. Okay, in CFD we usually have n in the range of 10 to the power 5 to 10 to the power 8. It is very common to have millions of degrees of million number of mesh points. Okay, so if we employ direct methods, we need to store. So if we employ direct methods, then we need to store 10 to the power 10 to 10 to the power 16 number of values in memory. Okay, so let us say one entry uses 8 bytes. Okay, so this is the size of the double in C++. So one entry requires 8 bytes. This requires 8 into 10 to the power 7 gigabyte of RAM in your computer. Okay, so this is not feasible. Okay, so and this is not the case in the current commercially available softwares. You can install Fluent or OpenFOAM in your laptop which has like 8 GB RAM, and you can solve CFD problem with at least 10 to the power 6 number of mesh points. Okay, such a thing is possible because we always employ direct methods. Okay, we always employ iterative methods in CFD. Okay, the major problem and once again I highlight, the major problems are the poor efficiency, okay, which says to larger computational time, and huge memory requirements, okay, which expects demand for high-end hardware. Okay, these are the major problems of what do we call direct methods of solving the system of linear algebraic equations. Okay, so we can even say that direct methods are never used in CFD. Okay, in general we can say that no CFD simulation package employs direct methods to solve the linear algebraic system arising from the discretization. Okay, so that is very clear for you because you are able to solve or perform simulations using your laptop that has just 4 to 8 GB of memory. Okay, whereas direct methods require a very huge amount of RAM. I'm not talking about hardware, I'm talking about the RAM. Okay, but although in general direct methods are never used in CFD, there is a special method called Thomas algorithm. Okay, this is one specific method that is commonly used in CFD. Okay, it is called Thomas algorithm, which is nothing but Gauss elimination applied to tri-diagonal matrix. So Gauss elimination applied to tri-diagonal matrix. Okay, so it is also called as tri-diagonal matrix algorithm. Okay, it's called TDMA. The Thomas algorithm is also called TDMA, which means tri-diagonal matrix algorithm. Okay, so remember that the discretization of steady one-dimensional heat conduction problem led to the following. We considered 5 nodes and we got a 5x5 matrix with this as the system matrix. Okay, you can go back and confirm this -1 1. Okay, so this is a sparse matrix in which non-zero elements are located only on 3 diagonals. Okay, so this has non-zero entries only on 3 diagonals. Okay, the main diagonal. Okay, so this is the main diagonal. Okay, and this is the lower diagonal, and the upper diagonal. Okay, upper diagonal. All other entries are 0 there. Okay, such matrices are called tri-diagonal matrices. Okay, so we have used only 5 nodes, but increasing this to 1000 nodes or million nodes will not change the structure of this matrix, but only increase the size, but not the tri-diagonal structure of the matrix will not be changed. Okay, so when Gauss elimination is applied to such special matrix, it gives rise to very powerful and very fast algorithm. Okay, so let us denote a general tri-diagonal matrix as follows. Okay, denote the general tri-diagonal matrix, okay, as follows. Okay, let us name the entries appearing in main diagonal as D, okay, and the upper diagonal as U, okay, and the lower diagonal as L. Okay, L2, L3, Ln. Okay, so when we apply Gauss elimination, the first step is the forward elimination. So we want to convert this tri-diagonal matrix into an upper diagonal matrix. Okay, which means that we need to just make the elements appearing in the lower diagonal to be 0. Okay, so if we take just row number 2, okay, if you multiply the elements of row the second diagonal by the second row by D1 and subtract it subtract the values of this one, then you will get L2 to be 0. Right, this is how Gauss elimination goes. So you perform these row operations. Okay, so L2 goes to 0 and D2 becomes D2 times D1 minus L2 times D1, and similarly the right hand side, which I missed here, is B2 times D1 minus B1 L2. Okay, we are multiplying the first row by L2 and subtracting the resulting value from row 2 times D1. Okay, so you can repeat this process for all the rows. Okay, the same process you repeat for all rows. In the end, you get an upper triangular matrix with only 2 diagonals. Okay, and the back substitution is very straightforward. Okay, so now I'm going to stop here, but what you have to do is you have to refer to any numerical methods book. So any numerical analysis or numerical methods book, and write the complete Thomas algorithm. Okay, yeah, please do that. And in the next video, we'll discuss about iterative methods. Thanks.